All right, so we looked at the A-star algorithm. Now here's an A-star world on Ancient Brain. So when I run this, I get a different problem each time. And the problem is to find the joint shortest path from the top left-hand corner to the bottom right-hand corner. And it can't go through these obstacles. There's only certain paths that it can actually take. So it has to get around these obstacles. And sometimes that's pretty hard, as we can see here, where the bottom corner was almost entirely blocked by obstacles. However, you can get through these diagonal paths here, these little cracks. So every time you reload it, you get a new problem. This is going to be a particularly easy one. And some of them, I think this one, can it get through? I think it can actually, but it's going to, no, it can't. How about that? So some of them, there actually is no solution. There's an impenetrable wall down here, and there is actually no way to get through in order to get to the goal. And that's pretty interesting. It's also interesting how many squares it has to look at before realizing there is no way through. As with all the other worlds, we want to check out, is there information in the console? Doesn't look like there's a lot going on in the console. Let's get rid of the console. So the other place where we can understand this, that one's interesting. Sorry, look at that one. No path exists. You have to search almost every square. But just there are the squares that it can't actually reach. That's fascinating. So the other place to learn about what's going on is obviously to look in the code. And the code, as with all these worlds, is available. You can clone it. You get your own copy. You can edit it, and you can start changing things. Now, one of the things that you might like to change immediately is whether a diagonal move is valid or not. You're going to see some radically different behavior if you say that diagonal moves are not allowed. Another thing you can do is you can change how many columns and rows that you can have, how many walls you can have in the middle. So you can set up all sorts of different mazes in this. It does have a lot of randomization in it, as you can see in the code. Every time you run it, that's an incredibly simple one. Every time you run it, there's randomization in the number of walls, there's randomization in the rows and columns, but you can change that randomization in the code yourself. So I encourage you to experiment with that. What else can we say about this world? There's one thing with the color coding. The black is a wall that you can't get through. The green are squares that we know about, but we haven't yet checked out what's beyond them. And then the pink are the squares that we've examined, and we've examined their neighbors. So we know all the neighbors of the pink, and we have full information about the pink squares. The green squares, we know they exist, but we haven't got there. Once we get there, we can see what their neighbors are like. So the thing about these white squares is the algorithm has figured out it doesn't even need to go there to see if there's a path to the goal. There could be a path to the goal via these white squares, but that path will actually be equal to or worse than existing known paths. So there's no point. We have a joint shortest path to the goal using the A-star algorithm along this route, and we don't have to search every square. That's the whole point of it. All right, so one further thing on the code is looking at the diagonal. We said we can turn this on or off, and that allows diagonal moves or doesn't allow diagonal moves. But this feeds in to the definition of the heuristic. The heuristic must always be optimistic. The heuristic is your distance to goal, and that must be optimistic. So if diagonal moves are allowed, that leads to a different heuristic than if they're not allowed. So if diagonal moves are allowed, the optimistic heuristic is the 2D distance. And I'll leave it to you to look at what the optimistic heuristic is if diagonal moves are not allowed. But it's crucial that the heuristic knows whether diagonal moves are allowed or not allowed. So have a look at that code. All right, and so to the exercise. There's a lot of things you can change in this world. The size of the world, the number of walls, the colors, you can go ahead and change all those. That'd be fun. One thing that is fun to change is if I search for frame rate. So frame rate would be nice to slow it down because it is running very fast by default, and it's kind of hard to see what it's doing. It's going into these various dead ends and giving up on them and trying a new route. If you slow it down, you really see what's happening. I'm not going to do that for you now because you have to have fun in your exercise. But what is frame rate? If I just double click on that and use our intelligent code help, we can go over to P5, and P5 will tell us about frame rate, which can be used. So it's a P5 thing to speed up worlds and slow them down. And in the exercise, you'll see a number of things you can change. One thing that might be fun to change would be to deliberately wreck it. Make the heuristic not optimistic, make it a bad heuristic, and see what happens to A star when you ruin it. So go ahead and do that. You can destroy these worlds as well as make them function better. And finally, there's quite a tricky question in the exercise, which is take the walls and turn them off. So that's easy. You make that to be 0. Take the diagonal and have no diagonals. Diagonals aren't allowed. So no walls and no diagonal. And then the question is, why is A star so unimpressive under those conditions? So you tell me in the comments, why does A star not work? So everything you need is in the exercise, so off you go.